Let me get started. I'm going to talk about counterfactual inference using unobserved confounding via exponential family. Most of the ideas here are primarily from graphical models technology, as I would call it. Putting it another way, what we're doing is we're using how to learn graphical models, undirected graphical models from very, very limited data, and explain that sort of how it can help, especially when there are confounders that are not observed. Okay. I'll make it sort of more precise as I go along. Joint work with Devavrat Shah, who is sitting there, and Raz Dwivedi, who is just sitting next to him, and Greg Warner, my colleague at MIT. Okay. So just to sort of set the context as to where we are coming from, this is a good caricature setting. So we're thinking of a sequential recommendation system where, you watch something, and you get something, and you watch some more, and you get some more. And now again, whose preferences are this among me, Abin, and Raz? That is good to guess. Okay, so that's you're sort of getting these things sequentially. Putting it other way, what's happening is that for a given individual, you're showing a sequence of recommendations or interventions, okay, and you're observing their engagement with that. And of course, there is some user's characteristic and maybe some characteristics associated with the system and all that. That's called all of those unknown things hidden into this common Z, which could be very high dimensional. And that is impacting what you see each time. If there is a sequential dependence, okay, and maybe there are covariates associated with each of that time steps that are observed. Okay, so this could be time of the day, or could be the whether you watch it on a laptop or whether you watch it on a device or whatnot. This is what was recommended, and this is what you did with it. Okay, so this is a nice caricature to explain what's going on there, and that's a reasonable, at least graphical, and we'll make it more precise by adding all the right parameterization and probably distribution. But that explains what's going on there. Okay, so far so good. So what are we trying to figure out? Well, we've got multiple individuals who've gone through multiple such sequences, and we got their outcomes. So that's what we have. And what are we trying to do? We're trying to understand, well, if the same individual were given different sequence of things, and for each one of them, what would the outcomes would have looked like? It's a simple question. It's a counterfactual question. Okay, and again, sort of since there are Z's that are unobserved, as we all know, and just to sort of warm ourselves up, let me just remind ourselves of one of the well-recorded example. What does a well-recorded example say? That there are a ton of data points that were connected. Each data point corresponds to, let's say, a different show and the comedy amount in that, and aggregate engagement level that it had perceived. And now sort of as comedy amount increased, engagement decreased. So now it must be really, really bad comedy. Or if it's a good comedy, maybe you would hope that it would not look like this, right? It would look more like this. Okay. And of course, as we know, this is a Simpson's paradox. What's going on here is that, yes, as you grow older, as all of us know, older ones, that sort of it goes in that direction, but still sort of within the group, it still continues to sort of engagement continues to grow with the amount of comedy. And so if we had accounted for this age as unobserved Z, then potentially we would have built different models, and then we would have got the right answers. And that's something is what we want to do here in the context of graphical models. So just working towards precise formalism now. So we have sequence of observations indexed by n. So I or indexed by I, n of them. Each one corresponds to a user. These observations are generated under a sequence of interventions. For each of the setting, there are some of the observed covariate, or maybe none. And then there is something that's not observed. And the way they're sort of impacting this is these are the covariates unobserved and observed, which are impacting both what interventions are chosen and what the outcomes are. And really what we would like to do is that if we change this, what the outcome would look like, and to account for that, we will have to figure out Z, because otherwise sort of we'll be in trouble. We'll be in trouble exactly like what I showed you in previous example. And to some extent, we don't really need to figure out Z. All we need to figure out is that how it's impacting the effective distribution. Any questions?
So then everything looks good to me, except the independent user.
So what that means is that when you go to Netflix and whatever you're getting, and what when David goes to Netflix, whatever he's getting, yes, they are also have correlation, but given what you observe at the end of the given intervention, what you're saying, your outcome condition on those things is independent of what David's outcome would be. So which is, unless sort of if you and David are sitting next to each other and say, hey, David, I'm watching this right now, and you instantly tell him, and then sort of that influence. So I'm avoiding that.
What is the model for intervention? So is the intervention is something chosen by the user, or that fits in, or this even distracted?
So at some level, sort of there is no real model as per se, other than the fact that there is some unobserved phenomena, let's call it algorithm and many other things, that determines that. And there's a specific way I will model it in a second.
But it's a function of observed and unobserved covariance.
Yes. Okay. Maybe this is exactly your question suggesting let's make it precise. So let's do that. So I'll do that in a second, but just to, I'm working towards that. The question that now we are interested in is for every user I want to know what would happen to the outcomes if different interventions were given. Well, I want to keep those unobserved characteristics the same. And of course, I want to keep the observed covariates the same too. Okay. Putting it another way, I'm trying to understand the conditional distribution of Y when I'm going to change A while keeping these two things fixed. So there is already I'm imposing an assumption here, right? That is, all the collectively users are obeying similar conditional distributions. The things that are changing for users are these things, but everything else is coming from the same family. And now we'll make it more parametric. Okay, and again, so if we view this as class of distributions coming from the same family, then we are looking at sort of n different distributions. So now this is a precise form. So I want to use exponential family, or what in graphical model language will be pairwise graphical model. Okay, so it's a first order statistics and second order statistics. Effectively saying that I'm interested in the world of exponential in simplest setting, the means and the covariances, right? But a more complicated version would be generic second order. And so there I've got parameters, let's call it phi and theta, sorry, phi and psi. Am I pronouncing right? Okay, let's not try to pronounce the variable W is just tuple of all four things. And if I were to just spell it out for the distribution that I'm interested in for every I, now it looks something like this. And let's just slowly parse it in terms of what the color coding is. So I've got the quadratic form for observation. Then I've got this linear form for how A interacts with Y through this parameter. Then there is this green part, right? which is different effectively for different users. Again, this is common, but let's call this whole thing as a sort of a linear term or linear parameter associated with y. And that varies with every user. And the way it's varying with every user is there's some dependence on covariates, some dependence on unobserved things, and of course, there is a thing with y. So that means that now what I have is I've got, for each user, I've got one distribution from an exponential family or pairwise graphical model. They're different, they have some commonality and some differences. There is a quadratic term is the same, that linear terms are different. And now I want to learn all of them simultaneously.
What is the assumption that the quadratic term is the same is just for convenience?
So that came out because of this modeling assumption. Because of this modeling assumption, and exponentials, nice thing about exponential, if you condition that it still remain exponential, and sort of the parameter transfer. And so now we have the situation like this, that let's call these terms as capital theta, which are dealing with all the observed part of the model. And then there is this part, which is dealing with unobserved part. And that's a linear term, so we keep that separate. And so what I've done is now taken the original model and reparameterized it. So again, in the context of the classical pairwise graphical model, these are node potentials, these are edge potentials, right? And edge potentials across all n things are shared. Node potentials across all n things are changing. And the way they're changing because of the unobserved confounders. Any questions? And for n units, effectively now I have the following setting. There's common capital theta, different small theta, common edge parameters, different node parameters. If suppose all z's were the same, okay, there's no different confounders, which is effectively there's nothing to worry about. Okay, then these are the same thetas. So now we have n samples coming from same pairwise graphical model. And for example, in that setting, Guy sitting there had a beautiful result, which got started a sequence of works. And sort of this problem has been seen a lot of progress. Okay. If we have suppose just one sample is, n is 1, so we still have pairwise graphical model. Is there a hope to learn these things, right? On one hand, it looks hopeless, but on the other hand, if we go back to our, there's a graphical model 000, which is linear Gaussian systems, aka Kalman filter style view of the world. Well, the nice thing is that in that setting, we know that it's a stable system. And we also know that the xt plus 1 given xt is obeys the same conditional parameterization across all t's, which means that even though we might have a single observation, we're still able to learn it, right? And the reason we are able to learn it is because there is a lot, the effective complexity of the entire parameter class is a lot small. Using that intuition, and that was beautifully formalized by work by Kandiros, Kostas Daskalakis, and other collaborators. Okay. In that work, what they assumed is that this one is known, but theta, the node parameters are not known. Okay. Very, very nice work, actually. One nice thing that comes out, which I thought was really neat, especially as a technique to know, is as we know in this kind of world, one of the things we always like to do is have these kind of contraction property or Dobrushin-like condition. They're a nice trick where they show that effectively, if you don't have that, you can construct these multiple sub-problems, which will have something to do with eventually your problem of interest. but each subproblem has contraction property. It's a very nice argument, and we use that. Right? So that's something to. This work had put out a nice loss function that we will utilize, and there's a sort of very nice properties that is there. Like when Woofre et al. They were speaking at earlier workshop. We didn't call it GRAMSIA, but now in hindsight, we should have called it GRAMSIA Intermediate. It was a small workshop at MIT a few years ago. Is a part of Fort C, a precursor of Fort C, and there's sort of there's a nice presentation there, which I think Guy, you and others are organized, if I remember. Yeah. Okay. So what we are looking at is neither of those two, but somehow sort of putting the complexity of those two and simplicity of those two. So we have n things, each one of them is changing, but we have common theta. For each one of them, we have one sample, but we have n of them. Hopefully there's a sharing here. The question is, can we learn all of these things together? Okay. Question clear? Yes.
When you say one sample, you're talking about a whole trajectory over time. Is there a time dimension?
No, so now here there is a great point. So at some level, if y is one dimensional, it'll be very hard to do this. But if y is a higher dimensional, that is, I've got a higher dimensional observation, like the example I was showing in sequential recommendation system, then there is a hope to do this. Okay. All right, so we'll be interested in finding out these parameters and then use that to compute this expected potential outcome, as one would call it. Now, going from parameters to computing expectation in graphical models, we all know it's very hard, right? So we're not going to solve that hard problem. Okay. But the point is, if you have this, then you can compute it. What we'd like to do, that at least aside from computation, if you had sharp enough guarantees here, hopefully that would translate into sharp enough guarantee for this. That is an argument we make. Okay, so I'll just open this up. So again, we've got n data points like that, put through some loss function, and things will come out. So it's a clean optimization problem. What it would give us as a guarantee is that common parameters will learn really well as long as number of samples are larger than the log of the dimension, or dimension is of the y's and the v's, and scale is 1 over epsilon to power 4, and then per node parameter estimation for node wise. So per sample parameter estimation for node wise things would scale like this, and there the dependence would be polynomial in dimension rather than logarithmic. It'll depend on the metric entropy of the parameter space in which things live. And then, of course, dependence epsilon to power 4. Okay. So just to translate what this would look like for something interesting. So let's imagine that we know that these thetas, underlying thetas, are coming from space of k known, so linear combination of space of k known vectors, where each of the vector is sparse. In that case, this would scale like S log k. And since this is going to be large dimensional, the effective error or normalized error 1 over square root of p would look like S log k divided by square root of p. So those are the results. And before I go further, if at least I have communicated results, you will have something to remember. Yes.
So the dimension you said of theta star, that's the dimension in the bound of it as well.
That's correct. So this dimension includes the dimension of y and dimension of v's. So those are the observed quantities. Any other question? Okay. And again, so as I mentioned, we'll assume that there exists computational engine that does exactly the right thing. Then that will lead to, if you wanted to compute this expected potential outcome, the error would be scaling, for example, the same setting like this. So it will decrease with dimensionality. It'll have dependence on the how complex the underlying parametric space is, because you're trying to learn that from one sample. And there's an epsilon square sitting here. Okay. Now, there's one thing, it's sort of this epsilon 4, we believe it should be epsilon squared. We don't have the proof. Okay. Okay. All right. Now, this is all good. I'd like to sort of walk you through one interesting application, and then sort of at least a little bit about what the loss function looks like, why it's interesting, and then the rest we'll see how much I can get through. Okay, so here's think of the following sample. So forget Z's for a second. So let's say I've got n samples. Okay, for half of them, I know the covariate. So let's say typically an empirical econometrician who's trying to do some causal inference would say, forget about Z's. I know what covariates matter. I'm going to use them, and so based on that, I will do some downstream analysis, call it IPW or whatever. Okay. So first, what you want to do is you want to understand what those covariates are. So it's like you go and survey people hypothetically and find out their covariates. Half of them have given you their covariates, other half you can't find them. Okay. And so let's say for what you're observing for each individual is covariate, which is this plus some error. For some half, you already know that the error is 0. For other half, you don't know what the error is, but say, let's say it's bounded in some form. Here I'm thinking of it bounded in some S basis. And now I want to sort of impute this covariates. Okay. So I don't know these, but I want to impute them. And if you obey the same model, what will turn out is that you'll be able to sort of estimate these covariates for every I with this much error. Okay. So as long as n scales like this, we'll be able to sort of do that. So if you know that world of matrix completion, right? This is another way to do matrix completion. Okay. And so again, so if somebody thinks that graphical models may not have interesting things to say, maybe we should think twice. All right. Any question about this example? All right. So in remaining time, what I want to do is I want to just talk about what the loss function is and why is it interesting. I don't think we'll get the time to go through all the details. Yes.
That those scaling factors have to be.
So the short answer is yes. Okay. And that's what was bothering us, because then sort of what's the point? Right. And so this was an application that we spent time trying to figure out to say, well, at least there's one example where I know this is something that I can actually do something with it in reality. I mean, so theorems are always nice, but sometimes it's nice to see something you can do. In this case, the K vectors are coming because of the fact that I know that sort of what is the, I mean, I'm observing these, so I know sort of what dimension they're living in. In a sense, they're coming from the fact that each of the coordinate, right, is, so if I think of sort of error as a 0, 1 hypothetically, then each of the coordinate is one of the vector. Now I've got dimension D, so or dimension, that's where log dimension, so log K, and S is the sparsity. Thanks. Okay. All right. So the loss function and why it works. So again, because it's exponential family, at the end of the day, you're estimating parameters. So why not just do maximum likelihood? Of course, it is not the right answer, but with computation, it will be hard. So how do you do otherwise? So you'll find the loss function which is actually a proper loss function. And the origin of this loss function, as I mentioned, is in work of Devavrat et al. It's really nice, actually. And we argue that it is actually a proper loss function and it has beautiful properties. Again, the shared parameter we're able to estimate because of they are shared across all samples. Is a quadratic parameters. And it's kind of interesting the way analysis works. It doesn't matter even though the node-wise parameters are different. Somehow, quadratic you can still learn. Okay, so it's something really nice happens there. And then to get to individualized parameters, I was telling you, think about simple linear system, stable linear system. You need some contraction, and using the other work that I mentioned, you can actually convert it to Dobrushin-like setting. And then there is, because of continuity, to argue that there is Hessian is nice enough so that you are sort of close enough to your learning. You need some form of log sub below. And this is something that Raz and Abin spent a ton of time. I remember the argument was that there's a great world here where sort of all the experts have figured out, some of them are sitting in the room, how to sort of deal with all sorts of log sub below. And all we were doing is we were just looking at things on the compact domain rather than sort of, let's say, R to power D. So it should be obvious. And that's the answer that Raz and Abin got from everyone. And finally, we realized that sort of something that everybody knew, but nobody knew the reference. So we thought we'll put it out there. So at least now we know one reference, the R appendix. But it was a good exercise in the overall process. All right, so we've got maybe 10 minutes or so, right? So I'll just go through explanation of what the loss function is and why is it proper, and rest will leave. Okay, so in a nutshell, here is the problem we are solving. Okay, and if I were to think about that in the context of our question, this is how it looks like. Now, if one talks about an exponential family, and if I have, let's say, classical and independent samples, and I want to learn that underlying parameter theta star, what I would say is that here is how my maximum likelihood would look. Okay, so it's maximizes the log likelihood or likelihood. Likelihood would have this form because I'm taking the log of that, and I've got partition function sitting here. Okay, and as we all know, if you take the gradient of it, this empirical mean of the statistics would show up, or sufficient statistics, and then actual mean under that choice of parameter at which you are computing the gradient. So if you find theta that sets sort of the gradient to 0, then we are doing the moment matching, like classical classroom stuff. And so we will find the right answer, okay, under appropriate conditions. In particular, theta star will be the one that will sort of match it, because hopefully we have enough samples, approximately enough samples. The perturbation around there will work it out, I suppose. So this is all good. And for these reasons, as we know, it's a long history, right? There's a consistent asymptotic normality, finite sample stuff is the asymptotically efficient, that is the right second order as well. The problem is we can't compute Z in general, and that's where actually the GRAMSIA is, right? So it's kind of nice to start here. Okay, so an alternative is a loss function that we'll describe. Okay, so this is the loss function. Again, as I mentioned, origins of it is in Devavrat et al.'s work. Kind of counterintuitive, right? Because here's what's happening. So remember, this is what we have, exponential. So do two mistakes. One is remove this, and then take that and add negative, and somehow believe that that's going to do right. just to, I mean, and actually third mistake is you also took multiplication and put addition. So like 3 errors, remove Z, add negative sign, and remove multiplication by addition. And somehow this is a nice loss function. That was their original argument in this specific context. And early on when we started, early on when Abin started his thesis, our question was that, why is this a good loss function to begin with? What does it have to do with the underlying problem? I mean, there was a nice proof that they had, which provided finite sample analysis in the specific graphical model context. Now, of course, there's a nice, it is convex minimization. So if you have constraints which are convex, then it will do the right thing. And question is it why? So here is a simple, okay, here is a simple observation that the minimizer of the loss function under, so let's say infinite data, that is with respect to the distribution. Okay, so so let's say you have, this is a loss function, this is empirical. Now, these observations are generated as per true underlying parameter, because we don't know that. If you have lots of data points, let's assume that this looks like this. That is this. So now if I minimize over theta this quantity, which is this, turns out that that's exactly same as minimizing KL divergence between it's a uniform distribution and a distribution from the same parametric family, but with a little twist. That is, previously we had this as a parametric family. Now it's theta star minus theta is how we are parameterizing the same parametric family. And of course, the minimizer here will be the one where this is uniform. So unless there is degeneracy, this will happen only when this is 0, which means that theta equals to theta star. So that's the thing, and maybe in 5 minutes I can sort of walk you through the proof, and then we're done. Any questions?
So point is now this addresses the computational aspect as well.
Yeah, so this will address the computational aspect. This will, because now we use effectively, this is maximum likelihood, but in different. So just borrow the whole technology. You get all the things you want. You want central limit theorem, finite sample analysis, of course, requires some work. You'll get consistency. Now, the interesting question, though, is that, okay, let me sort of go to the next slide and then come back to this, because you asked this question. So all of these things are there, but this one is missing. What if, now, and this depends on the flavor. I mean, if you come here, you want to answer this question. If you're sitting outside and you're not looked at this kind of class of question, you wonder what's the point. But with that as a caveat, right? So this one doesn't have asymptotic efficiency. It is not optimal with respect to second order in asymptotic sense. There's a nice counterexample that we have that yes, it won't be because it's not going to work. So question is that how far it is. There's a one type of question. Second is that forget about how far. Is there a way to can sort of satisfy all of these things? Is there any method in generic exponential family? Because this is for generic exponential family. Yeah.
So, one, so magic behind that is that we can bypass the difficult problem of computing statistic function because we have access to the samples from the distribution. But of course, producing the samples ourselves, we just believe that there are
Perfect.
But there is an alternative way to produce those samples by running a Markov chain of buffers and and this, which is easy to implement, right?
Yes.
Is there an extension of this optimality principle if the samples are generated from the buffers and
Okay, so that's a good point. So I guess so far I've not sort of spoken about anything finite sample, right? So since I'm in the world of asymptotic,
Yeah, I accept that.
so
Right.
so that's that. Now the question is that if you are in a finite world, are you sampling from what distribution are you sampling from?
I'm gonna run the global dynamics from the graphical model with ARIA, which I'm trying to learn.
Yeah.
Right. Where you want to say the sample, but the chain has the correct distribution, right? As in the invariant
Yeah,
distribution.
so I have, right. I have a sample,
But you
from-
don't
but it's not IIT samples, these are samples coming from starting from.
Yeah.
Some.
So something-
And updates done according to the kit.
So something like sort of what you, I, and Guy did in 2014.
Yes.
2014. Okay, so your point is that we have right local, what is it? We know the local parameterization correctly, but we do not know the, so let's say it's a generator.
It's correct, but just by doing this, incremental updates.
So, okay, very interesting. So I think maybe we're getting ahead of myself. I'm getting ahead of myself, but assuming that locally things are correct, and let's say it's a sparse graphical model, then many of these, the way one would try to learn local parameters from that is by solving some kind of a local loss function. And there might be a hope there. Okay, so it's a great question. Yeah, okay. Because all you want is that local conditionals are correct, not global. And if you get the local conditional correct, then I've got a slide here later, which would actually lead to the right answer. This is a great question. Thanks. Okay, I'll do this one proof and then we'll be done because I'm almost at the end of it.
We end at 11:50.
Oh, I have 10 more minutes.
For you, 10.
No, I'm not sure sort of. Okay, fine. All right. I'll be polite and I'll take 5. Okay, so here's a simple proof. So again, we're going to argue that. So let's just remind ourselves, this is the left-hand side. Okay. Now let's look at the right-hand side, in particular this one. What is this? This is same as before. Instead of theta, now it's theta star minus theta. Okay. So now I take e to power theta star transpose fx out, and then normalize it by normalization, divide by normalization because constant corresponding to theta star gives me this. Okay, here, okay, this is a different x. Let's call it x twiddle so that we don't confuse it with this. We do the same thing, but normalization constant is a constant we multiply here. So we got this. Okay, so now this one is nothing but that. So now I've got this distribution looking like the ratio of this multiplied by exponential divided by the quantity of my interest. Now we put sort of in the KL divergence. Effectively, this is what I'm getting because the numerator goes down and hence this one goes up, and then I've got the uniform density there. Divide it into, because of the log and expectation. So this is one term. This is the next term. And then the third term is this one, which is just theta transpose fx. Okay. Now, let's assume for a second that these statistics are such that with respect to uniform, they are centralized. That is the 0. Okay. And this is effectively parameter independent, right? Because this is about underlying statistics. Maybe we can sort of shift things appropriately. And hence, this is not a terrible condition. Okay, so if that is the case, this is gone. Once it's gone, this is the only term that depends on theta. So which means that minimization of KL divergence is same as minimization of this. We are done. Okay. Any questions? All right. So thinking in the context of generic exponential family, the error decays like number of samples to power of 1/4, which we believe it should be 1/2. Our proof is only restricted to 1/4. Okay, so it's an interesting opportunity. And again, the way it would go is it will primarily do the concentration of gradient, and you want to get effectively nice lower bound on Hessian. Okay, and it's nothing complicated. Right. If we were to do in the context of same thing in the context of now apply for undirected graphical model. Again, I think this is where David, coming back to your comment that what you would like to do is for every variable, you're trying to compute its own parameters. There is a known parameters in terms of its node parameter and its edge parameters. And edge parameters are, of course, very sparse. Node parameter is just one. Let's say it's one dimensional, right? Then this is a local exponential family that we are solving. And the corresponding loss function would look like this, where it has got its own local version of pairwise thing, and this one. So as long as this conditional is right, which could be right in the context of if the dynamics is done right, then we will have sort of the right right loss function. Okay. And if you have right loss function, then it will work out. Okay, and again, so the way the argument would go is that first you would learn the common things first, and then you would learn the node-wise things. Okay, so you learn this sort of the pairwise parameters first, put that estimate, then sort of solve for node-wise parameter, and then sort of the arguments will go through. Back to our setting again, the way this worked is that theta was common across n samples, and somehow sort of even though this one changed, okay, I'll skip all of that. Okay, so while across all the samples, this was fixed, this changed, but I can still aggregate over n things, and the way calculations will go through, you'll be able to learn the pairwise parameters correctly, even though node-wise parameter could be literally so terrible. And it will get you right guarantee. Once you get that, for each node you go and look at each sample independently, as if now you're looking at the setting of the Daskalakis et al. You've got n different samples, each with well understood edgewise parameters, but per sample you want to learn the node parameter, and that's where sort of you do some work, and then we get sort of some bounds like that. Right, I've taken my 5 polite minutes. So that's a summary that I sort of broadly discussed before. Here again, sort of a little sort of annoying part here is that there is that metric entropy that shows up, and metric entropy of a space depends on your knowledge of the space, right? If you know nothing about it, it's too large. If you know a lot about it, maybe what's the point? So, so the question sort of kind of continues to annoy us. Don't think so you can get rid of that, because that's the nature of the problem. So you'll sort of somebody asks the right question here, hopefully we'll sort of we'll continue to suffer with that. And last but not the least, if somebody's interested, I think epsilon to 4 should go to epsilon square. All right, so with that, let me stop. Thank you.